A faint whisper just slipped past one of the most powerful radio ears on Earth, and almost nobody noticed. It came from the closest star to our sun, a red dwarf that sits only 4 light years from your bed tonight, a place we have been listening to for years, hoping for nothing, hoping for everything. It should not have been there. And yet it was. This is the story of the signal Earth still cannot explain. Welcome back to the channel. If stories like this one are why you are here, hit subscribe and turn on the bell so you do not miss what we find next. To understand why this signal matters, you have to go back to 1977. It was a quiet night at the Big Ear Radio Telescope in Ohio. A graduate student named Jerry Amon was scrolling through reams of computer printouts, the kind of green striped paper the old machines used to spit out. He was looking for the regular hiss of the sky. He was looking for the predictable patterns of quasars and pulsars. He was not looking for anything special. And then he saw it. 62 seconds of a signal so strong, so narrow, so unlike anything the sky usually does, that he picked up a red pen and wrote one word next to the spike on the page. Wow. The wow signal became the most famous unexplained radio detection in the history of science. It came from the direction of Sagittarius. It lasted less than 2 minutes. It never repeated. Every attempt to find it again pointed the biggest radio dishes on Earth back at that exact patch of sky, and the sky stayed silent. For almost 50 years, the wow signal has been the gold standard of cosmic mysteries. Not because anyone thinks it was little green men. Most astronomers lean toward a natural explanation, a comet, a freak reflection, a glitch in the receiver chain we have not yet identified. But nobody has proved it, and nobody has explained it away for sure. It sits there in the data, a fingerprint from somewhere, half a century old, still waiting for a name. That fingerprint is why people like us still listen. And that brings us to the closest star in our neighborhood, the one that just quietly handed us something we still cannot fully explain. Proxima Centauri is a red dwarf, a small dim ember of a star, only about an eighth the mass of our sun, glowing in soft red light about 4.2 light years from Earth. In Milky Way terms, that is right next door. If the sun were a lamp on your desk, Proxima Centauri would be a candle in the apartment next door. Astronomers already knew Proxima Centauri had planets. In 2016, a team using the European Southern Observatory announced Proxima b, a rocky world sitting in the star's habitable zone, the not too hot, not too cold band where liquid water could exist on the surface. Then, in 2020, more planets showed up. One of them, Proxima d, is one of the lightest exoplanets ever measured. 3 worlds, all close to a small star, all at least theoretically interesting. So when a group of very wealthy scientists decided to spend $100 million buying telescope time to search for signals that could be technological, not natural, the project pointed one of its biggest antennas at Proxima Centauri almost immediately. The project is called Breakthrough Listen. It is the most serious, most expensive, most sustained search for narrowband radio signals that could be made by a technology, not a star, ever attempted. It is funded by Yuri Milner, the Russian-born billionaire and trained physicist who made his fortune in internet investing. It uses real radio dishes in Green Bank, West Virginia, in parks in Australia, and in other sites around the world. It also reanalyzes reams of archival data that nobody had bothered to crunch before, because, listen, campaigns are expensive, and the math is even more expensive. Breakthrough. Listen does not listen to the whole sky. It listens carefully to about 1,000 nearby stars. Stars with planets. Stars we can see clearly from the ground. Stars we might someday point a larger instrument at to follow up on a hint. Proxima Centauri has been near the top of that list since day one. 4 light years away, 3 confirmed planets. One of them, a rocky world in the habitable zone. The listen time on it is essentially free. And then something happened. In April and May of 2019, the Parkes Radio Telescope in Australia, also called Murray-Yang, focused in on Proxima Centauri for a routine observation run. Parkes is enormous. It is a 64-meter dish sitting in a sheep paddock in New South Wales. It has been one of the workhorse telescopes of radio astronomy since the 1960s. And time on it is a sacred resource. Breakthrough Listen's software combed through the data the way it always does, looking for narrowband signals, signals that sit on a thin sliver of frequency, the kind of pure tone a transmitter would put out, instead of the broad, smeared hiss that natural sources of radio waves tend to give off. And it found one. The signal sat at about 982 megahertz. That is a single frequency. Narrow, sharp, almost a perfect line. The strongest signals from natural objects in space, like pulsars spinning in tight little circles or fast radio bursts exploding from magnetars, are never that clean. They smear, they wobble, they cover a wide stretch of the dial. This one did not. Even more interesting, the signal drifted slightly in frequency over the 5 hours it was being recorded. The drift was tiny, but the direction of the drift matched almost exactly what you would expect if the signal were coming from a source moving with Proxima Centauri as the star and the Earth slowly change position relative to each other overnight. A natural signal from Earth would not drift that way, because Earth-based transmitters do not move like that. A signal truly from a distant star would. Inside breakthrough. Listen, this hit the red flag the way the WOW signal once did. They tagged it. They called it BLC-1. Breakthrough Listen, Candidate 1. The first signal from the project, serious enough to require that level of attention. They could not announce it publicly right away, or they had to first rule out every mundane explanation they could think of. They spent the next 18 months doing exactly that. And that is where the story gets strange in a new direction. Here is the first twist. Most narrowband signals that show up around real telescopes are local interference. A microwave oven that has not been turned off, a satellite phone, a radar station, a faulty refrigerator compressor. Parkes has been plagued by these for decades. The astronomers there have a nickname for the worst of them. They call them peridans, after a mythical winged deer, because they show up here and there almost like ghosts. The Breakthrough Listen team checked for peritons. They checked for cell towers. They checked for satellites. They checked for radar. They checked whether the signal showed up when the telescope was pointed away from Proxima, hoping to see it disappear, which would prove that it was coming from Proxima and not from somewhere on Earth. And here's the weird part. The signal did exactly that. The narrow tone appeared when Parkes was pointed at Proxima Centauri. The tone disappeared when Parkes swung away and pointed at empty sky. That is not what local interference does. Local interference usually shows up whenever the receiver is turned on, regardless of where the dish is pointing. And the more the team checked, the cleaner the signal looked. They eventually published their detailed analysis in the journal Nature Astronomy in 2021. Lead author Sophia Sheikh from the University of California, Berkeley. Peer-reviewed. The most careful, methodical document ever written about a possible alien radio signal. And it was honest. It said the signal had every feature you would want to see in a real technosignature, a sign of technology. It also said it was narrow. It also said it was drifting in the right way. It also said it only appeared when the telescope looked at Proxima Centauri. And then, in 2021, Breakthrough Listen released a follow-up after even more analysis, published in the same journal. They tried harder to find an Earth-based explanation. They tested multiple receivers. They did statistical studies. They looked for any pattern of when the signal appeared. The conclusion was that the signal was almost certainly a form of human-made interference that they still could not fully identify, most likely local electronics. But the team was honest about the limits. They said they could not rule out an extraterrestrial source 100%. They said the source of BLC-1 remained technically unconfirmed. The peer-reviewed paper by Sheikh and her colleagues explicitly stated that an extraterrestrial origin had not been fully ruled out. And that is where the story sat for a few years. A faint, narrow, perfectly drifting tone from the direction of the closest star to our sun, a signal that did everything right, a signal that could still be up there, repeating, on a slice of the radio spectrum, waiting for the next time a real telescope points at it. It did not make headlines. The WOW signal did in 1977 because there was one printout and one man with a red pen. BLC-1 did not because it lives in a different era. We live in an era of data pipelines and slow, careful peer review. The interesting signals get announced in journals, not on the evening news. And that is why almost nobody you know has ever heard of this one. Now here is why this story did not end in 2021. Here is the part nobody is telling you. In the years since BLC-1, while most people stopped paying attention, the rest of the sky has been getting louder. Not louder in noise. Louder in the kinds of signals we cannot explain. The cosmic microphone has been picking up stranger and stranger things. And the explanations have been getting thinner and thinner. Let me take you to March of 2025. On March 16th, 2025, a radio telescope array in British Columbia, the Canadian Hydrogen Intensity Mapping Experiment, also called CHIME, detected a flash. CHIME is built to listen for fast radio bursts, often called FRBs. These are short, intense blasts of radio waves that come from far away and last only a few milliseconds. Some of them come from neutron stars with enormously strong magnetic fields. Magnetars, the leftovers of massive stars that exploded and collapsed into objects so dense a teaspoon of their material weighs more than a mountain on Earth. We have known about FRBs since 2007. We have cataloged thousands. We have good models for the repeating ones. And then CHIME picked up something different. A flash so bright that for a few fractions of a second it outshone almost every other radio source in the sky. Astronomers named it FRB 2025's 316A. They nicknamed it RB Float. RB Float was not just bright. It was the brightest fast radio burst anyone had ever seen. And it was close. Not next door close. But about 130 million light years away in a galaxy called NGC 4141 in the direction of the Big Dipper. That is cosmic neighborhood distance. In a universe where most FRBs come from billions of light years away, this one was practically shouting at us from the next block of stars. It lasted about 1/5 of a second. Less than the blink of an eye, and then it stopped. Astronomers watched. They pointed every dish they had at that exact patch of sky for hundreds of hours, hundreds of times longer than the burst itself. They waited for it to repeat the way magnetars repeat their bursts. It did not repeat. Crickets. The KIME team, working with a network of outrigger antennas spread across North America, published their analysis in the astrophysical journal Letters in 2025. They said the burst was bright enough that some kind of cataclysmic event must have produced it, but the source did not look like any known repeater. It was an apparent one-off, a single shot, a blast that released more energy in a fifth of a second than our sun puts out in days, and then went quiet. Not a magnetar in the way we normally picture one, not a known kind of object, something we do not yet have a name for. A category, -1, as one of the researchers put it. Stop and sit with that for a second. In just a few years, we have gone from a possibly technological signal at the closest star to the brightest, closest, unexplained radio flash anyone has ever caught. Each one real, each one peer-reviewed, each one waiting for someone to explain it. And here is where the story takes the turn that should keep you up at night. 4 months after RBF float, on July 2nd, 2025, another kind of signal lit up a different set of instruments. And this one lasted not a fifth of a second. It lasted 7 hours. NASA's Fermi Gamma Ray Space Telescope, which has been circling the Earth since 2008, spotted the explosion. Gamma ray bursts, GRBs, are the brightest explosions in the universe. Most of them last a few seconds to a few minutes. They come from collapsing massive stars or from neutron stars colliding and merging in dense corners of galaxies far, far away. Fermi has cataloged around 15,000 GRBs over its long life. And so, when it caught a new one on July 2nd, 2025, it logged the event like it always does. The astronomers call this burst GRB 2507-2b. And as soon as they saw the data, they knew something was off. Most GRBs last minutes. This one kept going, and going, and going, for 7 straight hours. Think of what 7 hours means in cosmic time. Stars exist for billions of years. Galaxies exist for billions of years. 7 hours is a flash. Yet, in cosmic terms, a 7-hour gamma ray blast is practically geological. It is also nearly twice as long as the previous record holder for a gamma ray burst of this kind. And there is something else unusual about GRB 2507-2b. Most gamma ray bursts are one and done. The collapsing star pops once, and that is it. GRB 2507-2b flickered. Multiple peaks, multiple bursts within bursts, as if whatever was powering it kept turning itself on and off again over the course of a single July night in 2025. The signal came from about 8 billion light-years away in the direction of the constellation Scutum. 8 billion light-years means we are seeing it as it was when the universe was only about half its current age. Whatever made this explosion did it before our solar system existed. The light has been traveling toward us almost since the beginning of time. And nobody has agreed on what made it. Here is the second twist. There's a leading theory. The leading theory is that GRB 2507-2b came from the death of a star that was being eaten by a rare kind of black hole. Not a small black hole, not a supermassive black hole, something in between. The in-between kind is called an intermediate mass black hole, and they are some of the most mysterious objects in the universe, because almost no firm examples have ever been confirmed. If the in-between theory is right, then GRB 2507-2b is not just a record-setting GRB. It is also one of the first real pieces of evidence that intermediate mass black holes actually exist, that a whole class of cosmic object we suspected to be real might be real. But that is just a theory. And the truth is that the data does not quite line up with the in-between theory either. The shape of the burst, the energy of the burst, the chemistry of the light, there are parts that the in-between model does not explain well. NASA and a dozen teams around the world are still working on it. Papers have been written, papers have been argued over. A paper in late 2025 in collaboration with the Einstein probe team even hinted that GRB 2507-2b might require a second emission mechanism inside the explosion, a kind of engine inside the engine that the standard collapse model does not need. But as of this month, in the summer of 2026, GRB 2507-2b is still officially listed as unconfirmed in origin. 3 signals, 3 corners of the sky, 3 different mysteries. A possible narrowband technosignature from the nearest star system. A one-off radio flash from the closest FRB ever, blasting brighter than anything we had seen before. A 7-hour gamma ray burst from a half-formed universe, behaving in ways our best models cannot fully explain. If this were a novel, a screenwriter would tell you it is too much. Too many coincidences, too many open-ended signals in too short a window. But this is not a novel. This is the data. And the data is telling us, in 3 different voices, that we do not understand parts of the sky the way we thought we did. Here's what that means for you, sitting where you are tonight. When most people hear the words cosmic signal, they think of little green men and flying saucers. They imagine a clear story, a microphone, a tap on the shoulder, a clean confirmation. That is not how it works. That is not how it has ever worked. Science works in hints. Science works in quiet whispers. Science works in data that lives in a folder for years before someone notices the pattern. But here's the thing nobody says out loud. The number of confirmed, unexplained cosmic signals has been growing. Not by a little, by a lot. In the last decade, the catalog of fast radio bursts grew from 0 to thousands. The catalog of long-duration gamma ray bursts grew to include events like GRB 250702b. The catalog of candidate technosignatures, narrowband signals that pass our first round of tests, has grown to include BLC1 and others we have not talked about today. We are not in the middle of a quiet era. We are in the middle of an era of weird. And here's the part that should give you chills. Not the kind of chills from a horror movie. The kind of chills from realizing something bigger than you is bigger than you thought. Everything we know about the sky, every textbook, every documentary, every poster you grew up looking at, was built on the assumption that most cosmic signals have no natural explanations. Pulsars, quasars, colliding galaxies, magnetars, black holes collapsing matter. We are now living in a moment where that assumption is being quietly re-examined, not because of one signal, because of many signals from many instruments pointing at many parts of the sky all at once. That is how science shifts, not from a single startling headline, from a slow accumulation of anomalies that cluster until the cluster is too big to ignore. And we are at that point, right now. Summer of 2026, the cluster is here. Let me zoom out and bring this home because there is a meaning to all of this that goes beyond telescopes. When we say the word signal, we usually mean something intentional, something aimed, something sent on purpose by a sender trying to reach a receiver. And when we are honest with ourselves, that is the part that frightens people. The idea that something out there might be sending. The idea that we are not as alone as our calendars say we are. But the deeper meaning of this story is not whether we are alone or not. It is whether we are paying attention, whether we are still willing to listen, whether we are still willing to admit that the sky can still surprise us, even with the biggest instruments we have ever built. Even with 100 years of careful measurements behind us. Every generation has had its own version of this question. Did we just hear something from somewhere else? Are we sure? What does it mean? And every generation has answered it the same way. By building a bigger ear, a bigger dish, a more sensitive telescope, a wider net. That is what Breakthrough Listen is. A bigger ear, paid for by a billionaire, pointed at the closest stars we know. That is what KIME is. A bigger ear, built in a river valley in British Columbia, listening for fast radio bursts around the clock. That is what Fermi is, a bigger ear in orbit, watching the sky and gamma rays, waiting for the next biggest event. And the thing they keep telling us, year after year, is that the bigger our ear gets, the stranger the songs get. That is not a reason to be afraid. That is a reason to be excited, and a reason to make sure we keep listening. Because whenever the next signal arrives, and it will, we want our ear to be ready. We want to know what to look for. We want the data to be clean. We want our best people on it. We want them wide awake. And we want to be here, telling you about it. If this kind of story is what you come here for, subscribe now, and we are just getting started. Next year, the Square Kilometre Array in Australia and South Africa is going to come fully online, the most powerful radio telescope array humanity has ever built. Its job will be to listen for exactly these kinds of signals, plus a million more we have not thought to ask about yet. Whatever is whispering up there, we are about to give it the loudest microphone it has ever spoken into. You are watching this story at the exact halfway point. Not the beginning, not the end, the middle. And the middle feels like the right place to be, because we now know what to ask. We know the signals can be weak. We know they can be fast. We know they can be slow. We know they can be tiny and quiet and easily mistaken for local interference. We know they can be enormous and ancient and impossible to ignore. We know how to listen. We just need to keep doing it. Now, I want to do something with this ending that I rarely get to do. I want to zoom all the way out. Because every signal we have talked about tonight, every whisper from a nearby star, every flash from a distant galaxy, every hours-long explosion from a half-formed universe is a reminder of one quiet thing. We live in a universe that is not done introducing itself to us. We have been listening for less than 100 years. We have been listening carefully, with real instruments aimed at real targets for less than 70 years. We have been listening with computers, peer review, and software pipelines for less than 40. In cosmic time, that is nothing. That is the difference between one beat of a clock and the life of a star. The universe has had 13.8 billion years to send signals. We have had a blink to receive them. Every signal we have caught so far has been a lucky accident. We were pointing the right telescope at the right patch of sky at the right moment. The wild card was almost as big as the search. And yet here we are, 3 unexplained signals in 5 years. A directory of whispers growing louder. What if, 100 years from now, scientists look back at this moment and realize this was the decade when the whispers became a conversation? We do not know. We cannot know. But we can listen. And that is what we are doing. That is why I make these videos. To remind you that the sky is not done telling its story. That the next signal could come tonight. That someone in a control room somewhere could be writing the wow signal of our generation on a printout right now. That is the kind of universe we live in. Not a finished museum. A living, messy, throat-clearing patchwork of stars and signals and quiet waiting. And we are a small, curious, slightly sleep-deprived part of it, trying to listen better every year. If this story opened your ears a little wider tonight, leave me a comment with the signal you would most want to hear explained next. I read every single one, and the best ones feed directly into the next video we make together. If there is someone in your life who needs to remember that we live in a universe still full of quiet mysteries, share this with them. Send it to a friend, send it to your kid, send it to anyone who has ever looked up. Thank you so much for staying until the very end. The sky is not done, neither are we. I will see you in the next one.